A really great way to challenge yourself is to take a problem you already know and come up with a couple variations on it that change it and ask which ones of these do I know how to solve, which ones do I definitely not know how to solve, which ones do I need to think about more. So let's come up with some variations. So one thing you could think about was, sine and cosine are our kind of friendly, more familiar trig functions. What if you replaced them with something else? So instead of cosine, we've got tan. Or what if instead of inverse sine, we have inverse secant? And then this one's interesting also because you know that cosine and secant have a special relationship. So, does that create a special situation? What if the ordering of the regular trig function and the inverse were swapped? So what if I'm doing inverse on the outside and a regular trig function on the inside? It's one to think about. What if I was going to add something on the inside? So what if I have cosine of inverse sine cosine of inverse sine plus 5, or plus x, or plus x squared, or plus another inverse sine, or plus inverse cosine? You could imagine a lot of things here. Could you still solve the problem? So I think each of these is interesting to think about. I want to focus on this one right now for our purposes. So since we've got a new problem, go back to that first video. Remember that strategy? Remember the problem-solving strategy? What was it? I wanted to know what's making this difficult and say this would be easy if. And a lot of doing that is taking a problem that's slightly different and turning it into a problem that you already know how to do. So we actually made this problem by swapping where the inverse was. Inverse used to be on the inside. We know how to solve that. Now the inverse is on the outside. So could we do something here that would make that happen? Could we get rid of the inverse on the outside and somehow make it be on the inside? Let's name it A. The thing we're interested in is A. What could you do? What could you do to this that would transform the problem so that it looked a little bit different and it didn't have this uncomfortable feature to it? Let's see. I can't square anything because I'd be squaring this outside one, the inverse function, and we don't know any identities that have to do with that. I guess I could rewrite this inside function as square root of sine squared and then substitute on the inside, but that's going to be awkward because then I'll have this square root here that I won't know how to deal with. Instead, let's do this. Let's get rid of the thing I really don't like is the inverse trig function on the outside here. Let's get rid of it. If I take cosine of both sides, now these have undone each other, and so now I've got sine x equals cosine A. But what is A, we wonder? Let's try and create a geometric model here. So sine x, so x must be an angle, the way that I have it labeled here. So let's just give it, just to show that this works anyway, let's make this the angle up here, because it doesn't really matter where you put your angle. What matters is that all the information in your triangle is consistent with your equation. Okay, so what do we know about sine x? We know that sine x is telling us an opposite over a hypotenuse. So let's go ahead and label that. Here's opposite over hypotenuse. All right, cool. So cosine A, what's that? So we don't know what A is. We know A is supposed to be an angle somehow. What would this describe? This would describe cosine cosine is going to be adjacent over hypotenuse. But remember, it's going to be adjacent to some angle A, so it's not going to be adjacent to this x, unless x equals A. But it seems pretty clear that's not the case. So let's try on an interpretation. Like, we really only have one other angle here. Would it work if this was A? So here I've got A. Now this side is the adjacent side to A. This side's the hypotenuse. So that seemed like it's consistent because when this is x, sine x is giving us this side over this side. If this is A, cosine A is also giving us this side over this side. And here I've got an equals sign telling me these should be equal. So I've got a triangle where everything's consistent. Okay, so what was I trying to find here? I was trying to find A, right? So what is A? You might feel like we're stuck here because, like, we want to be able to write A equals and then something with some x's, right? And there doesn't seem to be any algebraic thing we can do. But again, using the geometric model, you're trying to focus on the meanings of things. So A is an angle. We actually now know which angle it is. It's this angle, where that angle's x. So the question is, if that angle's x, could you write what this angle is in terms of x? And the answer is definitely, because you know all these angles add up to 180 degrees. So you know that A is just 90 degrees minus x, or if we're going to be writing it more properly, let's use radians. So pi over 2 radians minus x. And A was this thing over here, so actually we've solved it. Now we know that inverse cosine of sine of x is just pi over 2 minus x. So again, we've simplified it. So there's one more note to make here, and maybe we should have made this note earlier. Let's graph both sides of this. Let's graph the left-hand side and the right-hand side, and you'll see an important thing. So here's the left-hand side, inverse cosine of sine of x. Here's the right-hand side that we simplified, and we see that they are, in fact, the same as long as as long as the angle is between these two values here. So what's going on? Remember that the output of the sine function has to be between -1 and +1. And if you consider this to be the input to inverse cosine, that means the input to inverse cosine is between -1 and +1, which it should be because those are the only valid inputs. But you see that inverse cosine also only outputs values between 0. Here's pi over 2, and this up here, this up here is pi. I was wondering if I was going to display it. So that means that there's sort of a range restriction here, which is this entire expression can only output values between 0 and pi. So if you want to put all that together, we just said that the output of inverse cosine is between 0 and pi, which means that this right-hand side expression is also between 0 and pi. Let's write that down. So if I subtract pi over 2 from all the sides of the inequality here, now I've got negative pi over 2 less than or equal to negative x less than or equal to pi over 2. If I multiply everything by -1, that's going to flip all the inequalities. That's going to flip all of the other terms. I guess I'll write it this way. So I'll have pi over 2 is greater than or equal to x is greater than or equal to negative pi over 2. So in other words, the original input angle has a domain restriction of being between negative pi over 2 and pi over 2, and that's exactly where we see it lining up here. So that was sort of a technical detail I just wanted to clarify for you. And you can think about kind of similar domain restrictions for a lot of these other simplifications as well. But for our purposes today, I mostly wanted to focus on the problem-solving techniques for being able to interpret the expression using a geometric model that then you can reason your way to figuring out what you're trying to figure out.